So the next seminar on probability and stochastic process of iming, it's from Guilherme Reis. He took his PhD at IMPA and he's currently making a postdoc at the Federal University of Bahia. And he's going to speak about modeling ants. I will turn off your microphones. Okay. So,
thank you.
Thank you, Guilherme, for accepting the invitation, and now it's your turn.
Thank you, Aline, for the invitation. Thank you for organizing these meetings. Well, today we are going to talk about the anti-mill phenomenon. Here we have some motivation to explain how you get to this problem. So the probability group at UFBA, together with the neuroscience group of the physics department, wrote a research project. The name of the project was on random models for brain functional connectivity. And we were interested in modeling memory, reasoning, through stochastic models using EEG brain data. One insight of the project is to use the hypothesis that memory is described through attractive periodic orbits of a dynamical system. Okay. The aim was to obtain the semi-periodic behavior through random walk models. More specifically, a random walk that changed the environment, making it more probable to follow the same path again. Unfortunately, the project did not get funding, and we decided to focus on the somewhat simpler anti-mill phenomenon. Okay, and now I'm going to show a video of the phenomenon. So here, in this video, we are seeing the ants. Okay, and what happened here is that the ant leaves a smell, a pheromone, and the other ant follows this pheromone. And sometimes this goes wrong because they make a loop and get trapped. Okay, so here. And
I have a question, but I'm not sure if this is part of the work of only biology. Is there any reason? Because as far as I understood, the first one have to decide to go in a wrong direction, right?
Yeah.
And then the other ones go following. So there is any explanation, biological one, for this first one just going for the wrong direction or not?
It's because they are kind of exploring the environment, and the smell is very strong and goes wrong. Okay. So there are a lot of things on internet about this. Well, there are research on this from the biological point of view, and also people using this kind of behavior to build algorithms. For example, to find a shortest path, something like that. Okay. So this is the phenomenon, and the ants will be trapped here, and they eventually die for starvation. Okay. So in the video, there are some information, but I think we can go to the math behind it. So what's our goal? We want to build a probabilistic model with simple rules, such that we can observe in our model the emergence of the anti-mill behavior. Okay, we want to see the same behavior through a probabilistic model, and we do that using the framework of random walks. Okay, so let's see if my pen is working. Okay, it's working. So here we draw some vertices. Okay, so here we have 5 vertices, and we draw some edges. Okay, and we have a graph. And first, we are going to recall what's the simple random walk on a graph. So here, we have a jump. So the vertex A has 3 neighbors. Each choose one uniformly at random. So it's 1/3 the probability of going from A to B. B has only 2 neighbors. So the probability of B going to D is 1/2. And so on. D can go the vertex. Okay. Something going wrong here. So the vertex B, I'm not seeing my, okay. So this vertex has probability 1/2 to go back to B, okay? So this is the usual simple random walk in a general graph. Now we will generalize this construction. Again, we start with the same graph, but now we consider weights on each edge, okay? So we have a weight 2 between these 2 vertices, and so on. And now we are going to jump again as a simple random walk, but now it's a slightly different because the graph is weighted, okay? So here, my pen is here. So here, the vertex A, it has 3 neighbors with weights 2, 1, and 3. So the probability of going from A to B is 2, divided by the total of weights of the other neighbors, okay? So this is the simple random walk on a weighted graph. And from B to D is 2 over 2 plus 2, because this and this edge has 2 as weight. And going back from D to B is we have the weight 3 here, the weight 2 here, so it's 2 over 2 plus 3, okay? So this is the simple random walk on a weighted graph. And we need to generalize further this by considering weights changing in time, depending on the walker, okay? Let's see an example. Again, we have our graph, but now we are going to choose this rule to update the weight of the edge. The weights are given by 1 plus the number of times we visit the edge E. Okay, so for example, the initial weights, all of them are equal 1, because the number of times we visited it at time 0 is 0, because we did nothing up to now. And 0 plus 1, 1. Now we jump. We jump as a simple random walk in a weighted graph. But the difference now is that we need to update the weight. Okay? Since we visited this edge once, we need to add 1, okay, to its weight. And you jump again, and here you see the difference, right? Because we have the 2 that appear here, appear in the probability, and we update the weight again. And you jump again. And now we are using the new weight that you have here. And now you need to update this weight. It becomes 3, okay? So it's a random walk with weights evolving in time, depending on the walk. So here, let's see some results. Here we are going to make a jump on abstraction. We imagine that the weight of the edge, we count the number of visits, add 1, and now we raise to the power p. Okay, here p will be positive. Burgers Davis in 1990 proved in the case of the graph Z, okay, so it's this simple graph, that in this range of P, the walker is recurrent almost surely, so it goes back to the origin infinitely often. But if P is greater than 1, implies that almost surely the walker will visit a unique edge forever after a finite random time. So what's the drawing here? The walker starts to jump on Z, and eventually it finds a edge and go back and forth forever. Okay, is it clear? Okay, so this is what happens when P is greater than 1. And it took 13 years until they can prove the same result for more general graphs. Okay, and here assuming bounded degrees. Okay, so the same behavior appears in any graph with bounded degrees. This means that the walker starts to jump in the graph, and eventually it finds an edge and go back and forth in this edge. Okay, and in 2017, Codina Kotar e Deblina Tucker extended the previous results into two directions. First, generalizing the graph. The graph now can be locally finite, doesn't have to have bounded degree, and the weight instead of power p can be any function with this condition. Okay, with this condition. Okay, that is, well, it's trivially true for the power p when p is greater than 1. Okay, there is some nice results about recurrence versus transience. It's the case p equal 1. Okay, so the rate is only 1 plus the number of visits. And Robin Pimento showed that we have a phase transition on regular trees. Okay, so, and the degree needs to be at most 3. And we have recurrence or transience depending on the initial weights. On several years later, they showed that if the initial weights are sufficiently small, the walker is recurrent for every graph. Okay, but I did not find any result about transience. Okay, so this is the results about that model that I presented. Well, though interesting, the walker in the previous results does not exhibit the same behavior similar to the anti-mill phenomenon, because in the model I showed to you, the walker gets trapped in an edge, and the behavior we want to see is that it is trapped in a circuit, making something in this way. Okay, and the reason for this, roughly speaking, this is really very roughly, is that once you cross an edge, we increase the chance of crossing the same edge in the opposite direction. So, for example, suppose that we have this edge, and here we have 6. When you cross this, the walker starts somewhere. Once the edge, the walker crosses this edge, this weight goes to 7, and this increases the probability of going back. So, roughly speaking, this is the reason why you get trapped in an edge. And another thing that we are going to use is that the quantity visits to E does not take into account orientation. Okay, it's just the number of times we visit the edge, and doesn't matter if you go back and forth on the edge. But we are going to see how we are going to explore this. And the question, how to fix that? Now, finally, we are going to talk about the anti-ground walk. Here, I need to change the drawing because this is better, but it's the same graph. It is undirected in the sense that we don't have an orientation in the edges. And the first thing is to turn this graph in an oriented graph, but in a very natural way. We just take each edge and consider the two oriented edges that this edge has. Okay? And now we are going to consider a new rule. The weight at the oriented edge, we first count the number of visits that you at this edge, but now visits, it's how many times you go from here to here, and we need to subtract the number of times you go from here to here. Okay, this is the rule. We are going to see the example. So the initial weights are e to the 0, aka 1, and why it is e to the 0? Because, well, at time 0, we did not, nothing happened, so the number of visits is 0, okay? And we have e to the 0. And we jump as in a weighted graph, so all the possibilities of jump are this one, and this one, and all of them has e to the 0 as weight. So we chose this guy and divided by the total. Okay, but when you jump, we need to update. So we crossed this edge once on this direction, and the crossing of B from B to A is 0. So 1 minus 0 is 1. But since we are in the oriented case, when you change the orientation, we change also the sign. So this the weight of this edge from B to A is e to the minus 1. Okay. So because of that, when you jump from the probability of jumping from B to D is e to the 0 because of this weight, e to the minus 1 because this edge from B to A has 1 minus 1, e to the minus 1, and because of that we have this probability. Okay. And notice now that the probability of jumping from B to A will be e to the minus 1, e to the minus 1 plus e to the 0. So it's less probable that we are going back in the same edge. Okay. So here appears the first difference with the previous model. And since this weight is e to the 1, the weight of this edge from D to B is e to the minus 1, so the probability is this one, okay? So, but now when we update, this becomes 0, e to the 0. Why this happens? Well, we crossed B to D once, but we crossed D to B once also, and we need to discount this, okay? This will be, this minus sign here, it's essential, okay? So Dirk, Tertuliano, and myself, we proved for any graph, finite, that's not a tree, or in ZD, for the greater than 2, this is important to have at least one circuit, okay? And here we need that our graph have some circuit to be trapped, okay? On these cases, the anti-random walk, after some random time, will find a circuit and spin forever around it, okay? So here we really are seeing the phenomenon we wanted. So the walker starts to walk, and eventually it finds a circuit and spins forever there, never leaving the circuit. Okay? And this was for exponential case, okay? Because we take the weights and the weights involve the exponential function. And we have a working preparation, and we believe that we can do this for this function that is more, it's a weaker reinforcement because now it's polynomial. It's not to take the exponential, it's just to take the power p. And we have to consider something for negative, the numbers that appear here can be positive or negative. And then the first thing we did was to assume that the negative part is bounded, but we strongly believe that the result is true for a more general function W. For example, we can consider here to the power P, here to the power Q, and P minus Q greater than 1, okay? So we also believe we can do something like this. It's like the positive part is growing faster than the negative part, okay? And faster is in this sense. So, okay, so let's see ideas of the proof. Let's see some ideas for the case when the graph is finite, and later on I will comment the case on ZD. And for a vertex V, we define a good edge of V as the one that attains the maximum. So we have this quantity, the number of visits of the edge, and minus the number of visits to the reverse version of the edge. We collect these quantities. Some edge, the graph is finite, so this maximum is attained. If this maximum is attained, we call it the good edge. So V has its neighbors. We look for the maximum, and we call it a good edge. Okay, one vertex can have several good edges. We just need one. And why this notion is useful? Because the probability of the walker to follow a good edge is bounded from below by a quantity that only depends on the graph. Okay, it's kind of 1 over the maximum degree, something like that. Okay, and we call a circuit C good if C is made only of good edges. So each vertex, we have assumed that the C is a triangle. This vertex has several neighbors. We want that the edge of this vertex that belongs to the circuit is a good edge. The same for the others. So here we have a vertex of the circuit. It has several neighbors. We want that the neighbor, the edge of this vertex that belongs to the circuit is a good circuit. It's a good edge. Okay, so it's a condition that needs to hold in each of the vertices of the circuit. Okay, and if C is a good, the probability of the walker starting on a vertex of the circuit to follow this circuit forever is also bounded from below. It's important that this is positive and it is uniform, only depends on the graph. Okay, and here I will comment later, but here the function being the exponential is very important. Okay, and I will comment what goes wrong if you don't have this hypothesis. Okay, So the main idea here is that, well, following good edges, we can lower bound, and following good circuits, we also have a lower bound. We define here a kind of algorithm, a step by step, to make the walker being trapped. First, we ask that the anti-round walk starts to follow only good edges. So, where am my pointer? Here, okay. So what's going on here? The walker is here. This vertex has some neighbors. We want that the walker, we are constructing an event. We want that the walker follows only the good edge of this vertex. This other vertex has some neighbors, and we ask him to also follow its own good edge. Okay. There is some technology, something non-trivial to do, but it's doable. This will be a non-backtracking path. Okay. The good edge for this vertex is not this edge that was previously visited. Okay. Why this is useful? Since the graph is finite and the path is non-backtracking, it eventually closes a circuit, okay? Because it's a kind of exploration on the graph. And you are visiting vertex, we are not backtracking, eventually you close a circuit, okay? And since you are only following good edges, the circuit we close is a good circuit, okay? Then we ask to the end, follows, spin forever on the good circuit, okay? So again, we follow only good edges, we are not backtracking, eventually close a circuit, once this happens, we follow this circuit forever. Okay? And from the previous bounds, all these steps, using also the graph is finite, all these steps happens with probability bounded from below by a constant, and this constant only depends on the graph. And to finish the argument, we are going to use that the pair, the walker by itself is not Markovian because it depends on the past, all the past, okay? But the pair walker weights, it's a Markovian process because if you know the position of the walker and if you know the weights, then we know the transition probability. So the pair is Markovian, and using this, we have some kind of independence, and we call a success if the walker follows this algorithm, okay? But anytime it fails, you try it again, okay? And so a Borel-Contelli argument implies that eventually the walker follows the algorithm, okay? So basically, where am my pointer? My pointer is here. Basically, the walker is following the algorithm. It tries to get trapped, but it eventually, by some reason, escape from being trapped. And now he tries again. Fail, try again. And by Borel-Contelli, this eventually will succeed and it is trapped. Okay? So this is the idea of the proof for finite graphs. And now I'm going to show you the ZD case. Well, this is the drawing for Z2. And roughly speaking, we can couple the walker on ZD with a walker defined in a finite ball, and the radius will be random. Okay. how this works. Well, and if you can do the coupling, since the ball is finite, we are in the previous case, and the walker is trapped. Okay. How is the couple argument? The point here is that anytime you leave a finite ball, we have a positive probability of being trapped in a circuit. Okay, because well, the drawing here, like the walker follows this path, and anytime it leaves the ball, here it's the boundary of the ball. Okay, let's use another color. We have here the boundary of the ball. Once the walker leaves the boundary of the ball, he never visited any of these edges, so the probability of being trapped on this circuit is positive. The probability of being trapped there is at most delta for positive, and doesn't only depend on the dimension. So, but maybe it escaped from this ball and go further, but eventually he can also hit this ball. When he hits this bigger ball, he has also a positive probability of being trapped. Okay, so this shows that eventually it is confined in a ball, and if it is confined in a ball, we can recover from the previous case. Okay, so this is the idea for ZD. And let's see what goes wrong when you try to use the polynomial case. And the reason is very simple, I think. When you sum this power series, it behaves like e to the x, okay? So we start with an exponential function. We again have the exponential function on the right-hand side. But here, when you sum this power series, we lose one power. Okay, here we have power p, and here we are going to have power p minus 1. Okay, and how this appears? For the H graph, what is the H graph? It is this graph here. We can, it's the simple, it's one of the simple examples of graph that you can analyze this walker. The probability of being trapped on the circuit corresponding to y. Y here, it's the number of times you spin it around this circuit, and we have x is the crossing, is the number of times you spin around this part of the graph. And in the exponential case, the probability of being trapped on the circuit is lower bounded by this function, by exponential of minus e to the x minus y. If I is bigger, this is at least, well, if you assume this probability, I think it's e to the 1, something. I mean, I'm not good to do calculations right now, but I checked this before. You can believe on me, or do by head. If y is bigger than x, this is lower bounded by something. Okay. Meanwhile, in the polynomial case, the probability of being trapped, again, we have the same picture. We have this. The probability of being trapped on the left side is lower bounded by something very similar. exponential of minus x to the p divided by y to the p minus 1. But what goes wrong here is due to the fact that we have a p minus 1 here. When you take x to x equal y, we have x. And if x is big, this is very negative, so the exponential is very close to 0. So don't get the uniform bound. And the uniform bound is crucial to use the Borel-Cantelli argument. Okay? And that's it. Thanks.
Thank you, Guilherme. It's very nice to see the circuits going on. Everyone have any questions? Can open your microphone or right.
Yeah, I have.
Yes.
Go ahead, Daniel.
Okay, thank you. So Guilherme, thank you for the really nice talk. I have two questions actually. So the first question is, what's the typical size of the circuit that you get? Is it the case that you get the minimal circuit always, or actually you can get very big circuits actually?
I think that the short circuit is more probable to be trapped, but it's just intuition. I don't know. I have some ideas to formalize these, but I never get to this direction. But I think it's a nice question.
Yeah, I think yeah, because you were drawing always the triangle, so I was wondering if actually that was actually the case. So the second question is actually more a little bit about the interpretation of the results. So I was thinking that if you're assuming that actually the ants are trapped because of the pheromone, right? Let's say that this was the hypothesis. So it's a little bit weird that actually you have an asymmetry, right? Because you would expect that actually the pheromone would go in the both directions. Right? So it's more similar actually to the original reward random walk than your walk. So how you would explain actually this difference? Or
well, I don't know. It's a good question. And I don't know why the ant, for example, well, the ant doesn't follow its own smell, right?
That's a good point.
And I don't know why. And if someone knows, maybe it's a good explanation.
Yeah, no, I see. So maybe that's the reason for the asymmetry. I see.
Yeah.
I have a question.
Yeah.
Guilherme, first of all, congratulations for this nice work and representation. My name is Nikolai Kolev from the Institute of Mathematics. Assisting your representation, I am finding some parallel with so-called line integrals.
Line integrals.
Yes. Somehow line integral is zero when the path is zero. This means the work done is zero. The work done is zero.
The line integral is zero when the path
when the path is zero. The path is closed. Sorry. When the path is closed, the line integral is zero. So when you move to the ZD, this has some relation with what you tell. Moreover, you defined very nice weight function number of positive and negative visits. This has very nice interpretation of resistance of organism. Because somehow positive part is how to say the immune system, but the negative part is the external inflation. So very I'm finding some interesting relations with other notions which even not how to say, not occasional, not occasional. And also, I am feeling that using this Borel-Cantelli lemma is something very good, but it can be related with using of Blackwell theorem.
What theorem?
Blackwell theorem for the mean time of returns of random walks.
Okay.
This is a classical theorem of random walks. So probably this can help you in showing some limiting results, additional.
Nice. Because there are some regimes that you don't know yet what to do. Maybe.
But congratulations for your nice work, and I'll be happy to get your report because in fact, line integral is something very important because the line integral uniquely determines line integral is based on hazard gradient, and hazard gradient determines the most probable direction. The sum of components of hazard gradient determines the most probable direction in the next step. And this line integral uniquely determines the multivariate distribution. There is multivariate survival function is uniquely determined by line integral. It's given by exponent of this line integral when you have the path. When you have the path. This is classical result by Marshall 75.
Nice.
Guilherme, thank you very much, and sorry if I disturbed.
Thank you,
I'll be happy to get your result and to discuss if you are available, interested.
Yeah, sure. If you have time, please send me an email with the reference, or I can contact you also. And it would be nice to talk about this.
About this line integral, it was just accepted my paper, this probabilistic interpretation of line integral on discrete grids. I'll enter in contact with you, okay?
Okay, thank you, Nikolai.
And congratulations to Alini to this nice seminar. I'm assisting first time, but I'm absolutely satisfied, even without coffee. Best regards to everybody. Thank you.
Thank you.
Do you have any questions?
Yes, I have one, or perhaps two. Well, the first one is, well, first of all, let me also congratulate Guilherme for this
nice
work. And
I'm not saying your name is Luis Renato, right?
Yes, I'm Luis Renato Fontes. Yes. So my question is related to this the circuits. So if I understood, I'm sorry, perhaps I missed something, but if I understood well your argument, you showed that eventually, if it doesn't do anything else, it will get trapped in a circuit, right?
Yeah.
And, but can it do something else, perhaps, instead of that? A circuit of these maximal circuits, right? Can it get trapped in a circuit which is not maximum, or do something else?
I don't know. There is a paper that the guys use this kind of reinforcement to find short cycles, short paths, in graphs. So they do some rule to update the weights, and they first send one end. Maybe I can. They first send one end, and then they reinforce this path, and then they send another end and reinforce this path. And because maybe the two ends follow the same path and something that I don't understand. Eventually, this finds the shortest path. And one direction that I think you can try, it's one idea for the future, is to try to find the shortest circuit using this. I think this is interesting in combinatorics, for example, because they have the girth of a graph, the length of the shortest circuit, and maybe we can adapt these ideas to find also the shortest circuit. But as I said to Danielle, I think in this case it's more probable to get trapped in a short circuit than in a longest one. But I don't have any result in this direction. I don't know yet how to do this computation, but I think it's something that it's very interesting to say about the model.
Okay, so just another one then. So is it possible for two circuits to touch on an edge, or
you mean this?
Yeah, something like that, yeah.
We first, this is possible. We first studied the problem in this circle. Then we studied the problem here. Then we studied the problem here, and eventually we tried to do this, and it was very difficult. But eventually we get the result for any graph. So the circuits can touch and so on. This case is simple because the competition is only in one vertex. And here, when they share one edge, the competition is between this circuit and this one. And here we have also this big circuit, right? So here we have 3 circuits, and the problem gets, here we have lots of circuits, so it's very hard. But we find a way to manage.
So can it get the wings, or can it can oscillate from one circuit to another when they touch?
Can you repeat, please?
The question is whether there's a circuit that wanes, that gets all of the action after a while, or can you have the walker moving from one circuit to the other?
In this case of only one entity, this cannot happen. But for example, we are interested in considering several ends, right? Because the video is about several ends. And what I think that happens in several ends is that can happen that the ends get trapped in disjoint circuits.
I see. Okay, thank you.
Or either they are going to be trapped in disjoint circuits, or it is going to be trapped in the same circuit. Okay, this is for 2 ends. Mm-hmm. And so in 2 ends, I think you can see the phenomenon we are describing, that one end get trapped on this circuit, the other in this one, and now they need to be disjoint, or they both will be trapped in the same circuit.
Right. Okay, good. Thank you.
There's a question of Nicolai.
Are you saying that you think that only one ring is gonna win? Only one people is gonna win. Any other question?
I have a question. Hi, Guilherme. It's Daniel.
Hi, Daniel.
Just to understand, because my intuition says that this pheromone phenomenon, it kind of, well, if you'd think that this kind of pheromone, it would vanish, right, with time. Like, it gets weaker and weaker, and at some point the ant cannot sense it anymore. But it seems to me that for your model, it is really important that you have a memory of all history, because if you have finite memory, it seems possible that you won't reinforce some circuits enough for getting trapped, right?
Yeah.
Am I understanding correctly? Yeah, the question is kind of loose. It's just to ensure that here this infinite memory is really relevant and you cannot remove it at some any way.
I don't know yet, but last week I found a paper that they consider. Let me write somewhere. Because now we have this quantity, right? Visits minus visits to the opposite direction. One visit here, it's a sum, right? This one here, it's a sum. We can take the indicator, the times that the walker crossed the edge. And this will sum until time n, right? Because this quantity here depends on time, okay?
Okay.
We need to count the number of times the walker visited. Last week I saw a paper. I found this paper where it multiplies here by something like beta. So
okay,
it kind of use what you are suggesting, that the reinforcement is decaying on time. Okay.
Okay, so it would be a middle ground in which the memory is still infinite, but the influence of the weight. Okay, I see.
Yeah, it's something to try. I don't know yet how to do this, and this paper considered this, but in other setup, and it's kind of weird because the paper has 4 years and what's not published, so we don't know if the paper is true. But okay, but at least we have this mild assumption to do.
Okay,
but nice. It's a very nice question. Thank you.
And congratulations for the talk.
Thank you. Thanks for the help with the program.
Okay.
Another question?
Can I make a comment rather?
What?
Rather than a question. Both Daniels, thank you also, Guilherme, for your presentation.
What's your name?
Camila.
Camila. Hi, Camila.
Camila, I'm sorry.
No, that's okay.
Thank you. I really like the idea of the model, and I think you can even better justify not having back propagation, because both Daniels, questioned a bit about the pheromone trail, and the pheromones are released from the back of the ant, so from the hind part, but the pheromone is sensed from the front of the ant, from antennas. So that's probably why they wouldn't go back with their own scent, because they'd be sensing first, scent from the ant that's in front. So that'll probably be for you to. But then that means you're right. They wouldn't be going back.
Thank you for the.
Thank you very much.
Another question or comments? I have a question.
Yeah.
Because actually I have a look in the paper, at least the version in archive, and you have a beta, which is not this one, but you have a beta which actually models the stretch of your reinforcement, right? But my question is not about the beta specifically, but do you have any bounds or any idea or how gonna be the expected time for this being trapped in this circle? Because actually you have shown the existence, right? Like you're gonna be trapped.
Yeah.
An idea of expected time?
No, not yet.
that if you have a very strong beta, this should happen very fast, right?
Yeah,
Otherwise,
yeah.
A lot of reinforcement. Otherwise, something that.
Because okay, my pointer is here. Because we have several regimes here. The first one is when the function is each the beta x, okay, and for this case the beta doesn't play a important role, but when you look at the time, it can.
For the instance of this trapping, but I'm speaking about the speed. How much you have to expect until being trapped in a circle.
Yeah, but this question also makes sense here, because you can expect that this lasts more time to be trapped than in the exponential case, because the reinforcement is weaker, right? Yeah, but yeah, we don't know yet how. I think it's a very interesting question, but we don't. Up to now, we don't spend any time thinking about it.
Okay, if you don't have any other question or comments, let's thank Guilherme. Maybe we open we should have done this with the other things. Thank you.
Thank you everyone for being here.